Hey everyone. Okay, so this is our second video. And in this video, we're actually going to use more advanced graphics. We're going to do what's called exploratory data analysis, which is oftentimes referred to as EDA. I believe in the data camp modules, they also refer to as EDA. It may not have been in the intermediate module yet, but somewhere if you follow on with other modules in data camp, you'll hear the term EDA used, and it's just exploratory data analysis. In short, what it is the ability to load up a data file and start looking around at its contents so you can start to get a better understanding and feeling for what is contained in that data frame, and you can start making some decisions about how you want to analyze it. So that's what we're going to do. And we'll load up 5 libraries, and we'll use those 5 libraries to help us get the data file loaded and start poking around with it and taking a look at what's in it. So amongst the 5 libraries, we have Pandas. Because we are loading a data frame, we are loading a .csv file and putting it into a data frame. Pandas will allow us to do that with the read CSV function. We're also using matplotlib pyplot in order to create some kind of basic and more advanced plots. NumPy will be useful for us as we do some numeric manipulation, and that's what NumPy does so well. We'll also use a package called Seaborn for one of our more advanced, in this particular script, one of our more advanced graphics, because it allows better graphics. Where NumPy, or I'm sorry, Matplotlib pyplot, where that kind of is sort of your foundation for all your graphics, for all your plots that you do. Seaborn allows us to do a lot more and a lot more statistically based plots. And then, of course, we're going to use OS. We're going to import OS that allows us to set our working directory. And that's the very next thing that we do is we set the current working directory, because I need to make sure that this script is going to look in the right place to pull in my file. So that's what the OS CHDIR, it's changing directory. And without the OS library imported, this, of course, changing directory wouldn't work. So we're going to change directory, and it's going to be C \\users, my name, and then my documents directory, basically. And I've got that set. Once I've got that set, I'm going to, before I load my file, I'm going to do something, and I don't really have to do it here. I can do it throughout the script. But there is a limit on when you print out a data frame. There's a limit on what it's going to show you. And you'll see if you've ever printed out a data frame, it'll show you the first couple rows, and then it will give you ... and it will show you the last few rows. It doesn't show you the entire data frame. By default, Python truncates both the number of rows and the number of columns that it will show you in a data frame. This is a way around that. So we use the Pandas data frame. We set options for display, and we're going to set the maximum number of rows, and we're going to set the maximum number of columns. That way it will not truncate unless we exceed either one of those maximums. So once we've got those set, we can go ahead and read in our data file. Now we're going to set that data file to be equal to DF, which is short for data frame. And a lot of people use DF. Certainly we'll use DF in demonstrating different scripts, but it's really not the most useful name, and it's probably better to name it something that is actually something you'll remember what it is. And we're going to go use the pandas read_CSV to read in a file called bostonhousing.csv. Note that the title has to be in tick marks because it is in fact a string, and it will look in the directory that I set earlier, a couple lines above, and it will look for that exact match of a file name. If it finds it, it will load it into a data frame called DF. If it doesn't, it will let you know. So once we've got that loaded up, now I want to take a look at the first 3 rows. And this is kind of the first bit of visualization that we're going to do on our new data frame. The head method can be tagged onto the DF data frame to show us the first 3 rows of that data frame. Now, we're specifying 3 rows, which is why it's going to show us 3 rows. If we did not specify, we just left head with open and closed parens and nothing in between, it would give us 5 because that's the default. But in this case, we're only going to look for 3. So it does that. It gives us those top 3 rows. And then just to make sure that the file is complete and looks clean, sometimes files can get messed up partway through and they can be messed up or out of order at the end. We'll take a look at the last 3 rows to see if those look okay as well. So once we have those done, and I can scroll ahead and show you kind of what we see, we start to see the names of the fields. And these are the first 3 rows. We have crime, zone, industrial, proximity to the river, all these things that are about what this file is about, and that is 506 neighborhoods in the city of Boston. So for each neighborhood, indexed using a numeric index, we have parameters, things about crime rates, about industrial land, about the average number of rooms for houses in that neighborhood. We have the average age for houses in that neighborhood. And we have these things which are indicators of tax levels, it's parent to student ratio, these things that are all specified that have to do with these neighborhoods. The one that may be the most important is going to be the median value. Now, these median values, they could be in thousands. So it could be 24,000s, it could be in 10,000s. But what it's going to do is it's going to allow you to see kind of what the median value for houses in that neighborhood is. Then we can go back and look at, okay, what are the factors that actually are associated or related to that median value? So the median value could be something that's fairly low, and maybe that means that there's a higher crime rate, or maybe that means that the parent teacher ratio is higher. Could be that there's a lower percentage of people that have a lower economic status. So this is something that we can do with this data, and we learn all that. One, we have a data dictionary that was provided to us, but we also learn the format of it. We can see how the crime rate is looking in all the different neighborhoods that we're looking at. We can see, average number of rooms and the like. But this is the beginning of our exploratory data analysis, and we can look at, what we have in these rows. When we look at the end, we have row 503, 504, and 505. I said there was 506, but remember we're indexed at 0, so we start at 0. There really is 506, even though it only counts to 505. We're looking at the last three. It doesn't look like anything's really, all that different. Doesn't look like we're missing data. We don't have any not of numbers. We don't have anything that's going to cause us problems. So the data set looks okay. All right. So now that we have a better idea of what is in the data set, of the 14 columns that are in the data set, maybe we want to look at median value. Median value, again, is the median value of homes in that neighborhood. And we want to compare that to factors that are typically associated or correlated with things like the value of the house. What drives the value of a house? One of those things could be the average number of rooms, and the other thing could be the average age. The older the house, typically, the lower the median value. The lower the number of rooms, the lower median value. Higher rooms generally are associated with higher median values. So we're going to take a look and plot and see kind of how this looks. We have a hunch. We have a hunch that median value is going to be associated in some way or form with the number of rooms, average number of rooms, and average age. So we'll go ahead and set 3 variables. In this particular case, we're going to set variable x, y, and z to the row that is, in this particular case, median value. I should say the column that is median value. So the entire median value column is set to x. We do the same thing with y. Y is set to be equal to the entire column, all 506 values for room. And we do the same thing with z. So what we're doing is we're creating 3 series, and these series are indexed just like the rest of the data are. There's 0 through 505, and we have values for median value, room, and age. Now we can come through and we can start using these 3 columns, these 3 series, to start building plots. And where in our first plot we did a line plot, we're going to go back to the matplotlib pyplot library, and we are going to build scatter plots. Okay, and in this particular case, we're going to build scatter plot that is x and y. So we're going to look at median value versus room, and then we're going to come through and we're going to do it again. We're going to do median value versus age. So we first set it up. We don't do anything fancy. There's no labels, there's no legend, there's no nothing. It's just a scatter plot of x and y, and then we show it. And we do the same thing, do a scatter plot of x and z, and we show it. And this is what we get. This is our median value versus rooms. And it looks like, if you were to draw a trend line through this cloud of data points, it looks like there might be a relationship there. We'll mathematically confirm it when we run correlation, but it looks like there could be a relationship there, and that's starting to give us an idea of one of the factors that could be driving median value, and that is the average number of rooms. Okay? If we were wise and we had given ourselves labels, we would see down here is the median value, maybe in tens of thousands, and up here is the number of rooms. We have some houses, some neighborhoods where the average number of rooms is 3 or close to 3. And then we have other neighborhoods where the average number of rooms is higher, quite a bit higher. But in general, the higher the average number of rooms, the higher the median value of the homes in that neighborhood. Let's take a look at our next plot. This is the age of the house, and it's also the median value. Again, assuming we're using in tens of thousands. So This one doesn't show as much of a relationship. In fact, it shows what could be potentially looked at as maybe an opposite relationship. The older the house, the higher the value. So we're seeing a lot more things up here, 100 years old, 80 years old, and they tend to be kind of leaning towards maybe a little bit higher value. And it could, I suppose um, it could follow an assumption that maybe older houses over here, the older houses are worth less, but we've got older houses over here that are worth quite a bit more. And we've also got some of the newer homes down here that seem to be a little bit further on the value scale than those that are up here. What this basically is telling us is there's not a whole lot of relationship between these data points. It's not nice and clean like this one is. I mean, this is not exactly clean, but it's a lot cleaner than this one is. We may get some negative correlation here, which basically means the higher the age of the house, the lower the value, but we would have to go and confirm that mathematically. So we've got our two scatter plots done. That's great. But now we're going to look at correlation. And I want to know the actual values. So we're going to do a correlation of x and y. Well, what that basically is, it's going to calculate a correlation coefficient looking at median value in room. And if you remember, in basic statistics, correlation coefficient ranges from -1, where they're different always, to +1, where they're very similar. Um, so if we had a case where, and we don't, but if we did have a case where median value always went up a very specific and measurable amount when compared to room, then we would probably have a correlation coefficient that was close to the value of 1. If the median value changes completely independent of room, then we have a median value, or I'm sorry, a correlation coefficient of close to 0. And if we could see that when median value went up, the average number of rooms went down in a fairly predictive and static way, then that correlation would be closer to -1. So we're going to go ahead and run that correlation, and we're going to do another correlation, and this one's going to be x and z. So we're going to look at, first of all, median value in rooms and median value in age. And what do we get? The first one has a correlation of 0.6953. So that's a little on the closer to one side. We can round that up and call that 0.7. And that's what this looks like. It's a 0.7 correlation. And that stands to reason because we are looking at a relationship that seems to be when the rooms go up, the median value goes up. And so that seems like it makes good sense, right? But when we're looking at this one, we're seeing it's a negative correlation. So we would see a trend line that would go the opposite direction. Again, the higher the age of the house, the lower the value of the house, but it's a much lower value. So we're seeing that it's 0.37. If we round it up, it would be 0.38, which is not completely insignificant. There is some relationship there. It's just not as clean as the 0.7 that we see up here. Okay, so that's how we can mathematically confirm that the relationship exists between median value in rooms in this first case and median value and the age of the house in the second case. Let's go back up to our script and let's finish up. So now we're going to set up for something called a heat map. And when we do that, we are going to do a method, which is core. Now up here we used NumPy and we used the correlation coefficient and we fed it in the x and y coordinates. And that's fine if we want to just look at the relationship between those coordinates. But what we can also do is we can use a method called core, and we don't specify anything, and it will take every numeric value in DF, and it will run a correlation between every other numeric value in the data frame. So what we get is a giant matrix of correlation coefficients, which is great. That can be useful. And then we can also specify, in this particular case, we're specifying a figure size, and we're using the PLT, which is matplotlib pyplot, and we're using a method called figure. And in here, we're specifying the figure size to be 15 by 15. And the reason why we're doing that is because if we don't do that, the heat map that is going to show us the relationship of every variable to every other variable in the data set will be too small. So we specify that we want to run that as a 15 by 15, and it will give us the size that we want. The next command, I'm not going to go into more than just a couple of things because it is not the cleanest way to build a heat map. There are much cleaner ways to build a heat map, and you can look them up on cheat sheets. They're available online. But basically what we're doing is we're setting up a variable that's going to be equal to SNS. This is where we're using the Seaborn now, the Seaborn visualization package. It does statistics and visualization, and it's going to set up a heat map for us. Okay? It's going to use core. as its value because we specified core. Remember, core is the giant matrix of everything versus everything in our data set. So we'll use core. It sets specifics, it sets colors, it sets other things. And I just, like I said, there's much easier ways to run a heat map. And we probably won't use them much going forward. But if we do use them much, it's going to be using the simpler way to set it up. And let me just show you what we get. This is our heat map. Well, the color palette that we decided that we specified in our command is what governs the colors that we see. The annotation true says go ahead and show me the values. Other things that we set up a legend, we set everything that we needed here. Okay, so let's take a look at what we're looking at. The first variable we have is crime. Then we have zoning, we have industrial land, proximity to the river. And if you look down here, we have the same variables. They're just across the horizontal axis. So where we have a variable compared to itself, that correlation is always going to be 1. So you can see that crime versus crime is 1. And that's not interesting. But crime versus things like in number, the amount of industrial land is a correlation of 0.41. The amount of nitrous oxide that is in the soil in that neighborhood is 0.42. The accessibility to freeways, 0.63. Taxation, 0.58, which means the higher the crime, the higher the taxes, which is ironic. The lower status. And you can see these because of the colors, right? The colors on your scale over here run anywhere from +1, which is the darkest blue, to -1, which is the darkest kind of reddish sort of rust color. So we can start looking at things that are interesting. For example, the amount of, or the percentage of nitrous oxide that's found in the soil has got a 0.77 correlation to, I believe this is location to development, industrial land, or freeways. I can't remember the exact value for that particular variable. Well, let's look at one. Let's look at age when we actually know what it is. We see that age has 0.73 correlation to the amount of nitrous oxide, and it has a 0.64 correlation to the amount of industrial land that is not used for residence. And we have a couple of really high correlations here, and we can start looking at those. But the one we're mostly interested in is going to be median value. And remember, one of the original questions we had was, what are the drivers of median value? Well, we have median value here, and the median value is actually categorized in this data set. So again, not terribly interesting, but just know that that's what this column is. So here's median value, and we can go up. Median value has a very opposite relationship to the amount of families that are of lower economic status in that neighborhood. That makes sense. If we go up, we see a 0.7 correlation for the number of rooms, and we saw that already, remember, because we saw the 0.69 when we actually did the correlation coefficient. It has a couple of weak relationships, so zoning, and that's pretty much it. So we might look at the relationship that we want to look at, the one that's most important to us, could be if we're going to try to predict, now we're going to switch into predict mode, just kind of a prediction mindset. If we wanted to predict what the median value of homes were going to be in a particular neighborhood, we might look at the average number of rooms, because we know we have a fairly decent relationship between those two variables. And the average number of rooms could be used as a predictor for helping us determine what the median value of homes in that particular neighborhood is. So this is where the heat map becomes very useful, because we can actually start to look at these variables and see where they are more blue. That's interesting because there is a positive correlation, and where they are more kind of rust color, that is interesting because it is a negative correlation, right? So if we are doing prediction or predictive analytics, a heat map or correlations like this can be a valuable tool to help us find our predictor variables and our predicted variables. Now, we happen to have all of that information in this data set because every one of the fields in the 506 neighborhoods is populated. So we really could build a decent model. We just would apply the that decent model to future data that maybe we had partial data around the neighborhoods, or we had all of the data here, we just didn't have the median value. So we could then use the data, the relationship that we see here, to set up or build a model that would allow us to predict the median value. Okay, that's enough about this script. I've given you a copy of this script so you can play around with it. I think it will be good for you to load it up and work through it and see it. Oh, there's one last thing I didn't talk to you about, and that is you can save the configuration. You can save your figure. So this is the command actually, it's part of the matplotlib and it allows you to save your figure. It's going to save it to your working directory. It's going to save it to whatever you put into the tick marks. In this place, we'll call it mygraph.png. And you can also specify the dots per inch, the sort of pixelation or clarity of the graph. That's just another parameter on that. Okay, that's the second script. Here's what your assignment is going to be. I've given you two scripts. We've gone through two scripts. One of them is fairly simple. The other one's a little bit more complex where we load data and actually look at it. What I want you to do next is I will give you a third file. I want you to go through, and I'll specify this in the actual assignment itself, but I want you to go through, load the file, and start doing some exploratory data analysis. What can you learn about the file? And so your assignment will be to identify 4 things, possibly using graphics, probably using graphics, but you can use correlation as well. Identify 4 things that you can tell me about your file and make a list. Go into Microsoft Word, you could drop it in as a document. You could make it as a notebook and turn in your notebook. But just show me, so if you do that with a notebook, make sure that you document it correctly and clearly. But show me what you found out about your file. Show me what you've been able to learn. And you're going to be kind of on your own. I've given you some ideas. If you have any questions about things, for example, if you wanted to use histograms or box plots, which would be great ways to look at data, you can look those up in your textbook. Your Python textbook will show you how to do that, or you can look it up online. There's a million different resources. Or you can even go back to DataCamp, and DataCamp has visualization, EDA classes that you can run through. But again, 4 things that are interesting about the file, and that will be what you turn in. Okay, let me know if you have any questions.